thank you very much for this kind invitation, and also thanks to the organizers of this conference for inviting me. I'm already learning a great deal, and I expect to learn much more before I go home. So the title of my talk, in English it's Radiation Forcing Much Ado About Nothing. That's a pretty good German translation. And so I'm going to actually give a physics talk, so those of you who don't share my enthusiasm for physics terms, I hope you'll be patient, and perhaps you'll learn something that will be useful. So if I can have I hope this works, the first view graph. How does this advance? Oh, this way. So, we're talking about the alleged climate crisis, which is that the world is going to boil over like this pot of water on a stove. But of course, this is nonsense, but this is a good picture because it illustrates the three mechanisms of heat transfer, the main ones at least. And so we're familiar with all of these mechanisms from our everyday lives. For example, we feel convective cooling on a windy, cold winter day when the wind, gives you frostbite, and the harder the wind blows, the colder you get. We're familiar with radiant heating. If we go to the beach, on a nice summer day, we get nice and warm from the sunlight heating us directly. And finally, we're familiar with conduction. Conduction actually is very unusual in things involving climate or massive amounts of energy transfer over large scales, but occasionally you run into it. So for example, if you put a silver spoon into hot coffee, you can feel the spoon heating up very quickly. Silver is a very good conductor of heat and electricity too. They're related to each other. So we know of these three mechanisms, and all of them are involved, or at least convection and radiation are involved in Earth's climate. I mentioned that conduction is unusual, but there is one exception where conduction operates on a large scale, and I just mentioned it for academic interest, and that's white dwarf stars. Stars of the mass of the sun, when they finally burn out, of course that will take many billions of years for our sun, collapse into white dwarf stars where the matter is extremely dense, but it's very much like an enormous piece of silver where most of the heat is transferred by degenerate electrons. So you can think of a white dwarf as sort of the ultimate silver spoon. But one consequence of this is that let me see if this, I guess there's, does this have a pointer? Is there a pointer here? I'm not sure. Well, okay, doesn't matter. One consequence of this high conductivity of a dwarf star is that the temperature is almost constant throughout the star. That's very unusual. The Earth's temperature varies between, here on the top of the neighboring mountains by quite a bit, but it varies very, very little inside of a white dwarf. Now let's talk about other stars, including our own sun. Surely this has a pointer here. Let's see, does this work? No?
Laser.
Where is the laser pointer? This is it. Oh, this one, okay, got it. So here's the sun, and the sun is the ultimate source of the climate emergency because it's the sun that heats us, and supposedly increasing greenhouse gases will keep that heat trapped so efficiently that we're all going to boil over. But the sun itself exhibits two of the modes of heat transfer I mentioned. Deep inside the sun, the energy, the heat, is carried from the core by radiation. So there's very little movement of the plasma inside the core, and most of the heat is carried by X-rays. The outer parts of the sun, the parts that we can see, you shouldn't look at the sun, but you can look through, dense glass. The heat is carried by convection. So both types operate in the sun. Stars much smaller than the sun have no radiative zone at all, so all the heat is carried by convection, and stars that are much bigger generate so much heat in the center that the center is actually convective and not radiative like the sun. So there's a lot of interesting radiation transfer that originated in astrophysics and has been taken over by climate alarmists, but they remind me a little bit of the Sorcerer's Apprentice. You remember perhaps the movie where Mickey Mouse becomes the apprentice of a sorcerer, and he really doesn't know how sorcery works, and that has happened to a large extent to climate science. They know the words, but they don't really know the details. All right, so let's, why does this not advance? There, okay. It advanced twice. Okay. So the sun generates its energy by fusing hydrogen atoms together, actually protons together. This is a very, very slow process because it operates by making positrons and neutrinos at the same time as it's converting two hydrogens to a deuterium nucleus. This is extremely slow and inefficient. So that's why the sun can burn for billions of years without using up its fuel too quickly. The only product of this burning that gets out immediately are the neutrinos. So in this process, neutrinos are created. They can go right through the sun with very little stopping and reach the Earth. And 20 years ago, when I was Director of Energy Research at the Department of Energy, one of the main things we were supporting was trying to see these neutrinos coming in from the sun. They didn't show up. And so people were worried that maybe the sun had stopped burning. There didn't seem to be any neutrinos coming, and neutrinos come instantaneously. You wouldn't know from the heat of the sun because it takes hundreds of thousands of years for the heat to diffuse out. So if the sun stopped burning today, we wouldn't know it, except the neutrinos would stop. But fortunately, they did not stop. And so they're really there, but in the distance between the sun and the Earth, the neutrinos have actually transformed from the original electron neutrinos that were generated together with the positron to other the two other types of neutrinos, mu neutrinos and tau neutrinos. So there's a lot of very interesting physics associated with the sun itself, the thing that drives Earth's climate. The subsequent steps here are all very fast. These following steps are much like what happens in a hydrogen bomb, but this step is not. This is very slow. Well, Earth generates some internal heat, but it's very small. It's less than a watt per square meter, quite a bit less. And so most of the heating of the Earth's surface comes from the sun. So about half of the sunlight gets absorbed on the surface of the Earth, the dry land and the oceans. And we have to get rid of that by thermal radiation going back to space. But in the process of getting this heat energy back into space, the first 10 kilometers or so are in the troposphere, and there about half of the energy is carried by convection, just like the outer layers of the sun, and the other half is by radiation, like the radiation layer. So the Earth is a sort of a hybrid compared to the sun. It has both convection and radiation at the low layers where we live, but as you get higher and higher, more and more of the heat transfer is radiation. And of course, when you reach outer space, it has to be all radiation. So now, you might wonder how much energy does the sun generate? And people are often surprised at how little energy is generated in the core of the sun. So the number is 277 watts per square meter. That's about the same as a compost pile. So this is thermonuclear fusion. People say the sun is a controlled hydrogen bomb, but hydrogen bombs make a lot more energy than this. And we actually make a lot more energy than the sun does. You're just sitting here listening to these talks, you're making 3 or 4 times more energy than the core of the sun makes. But the difference between our body temperature and the temperature of this room is only about 20 Celsius, whereas the temperature between the core of the sun, which is generating less heat than we do, and the outside is 15 million Celsius. So the difference is that the sun is thermally insulated much better than we are. We are designed to get heat out as efficiently as possible. That's why we don't have any fur or feathers, you know. So humans are really good at getting rid of heat, and if that's not good enough, you can sweat and get moist convection. But the sun is much less efficient. Yes. Thank you. Can you hear me better now? Yeah, thanks. Okay, so temperature differences, and that's what we're worried about in the case of global warming, that the temperature is going to increase. Roughly speaking, they go very much like Ohm's law. You probably remember having to learn Ohm's law, even if you're not a physicist, but that says that the current that flows through a resistor, here's a resistor, goes like the difference in the voltages between the ends of the resistor. And so heat flow goes very much the same way. The heat flow, Q dot, goes like the difference in temperature. This is sometimes called Newton's law of cooling. This is not a very deep equation because, you know, the resistance is extremely complicated, but at least it gives you a starting point. So what global warming is supposed to do is to greatly increase the thermal resistance of the Earth, enough so that we notice the warming of the surface. So we're going to talk about how much greenhouse gases can really change this resistance are. They can't change it very much, it turns out. Lots less than people think. Okay, well, in physics, you usually like to start with fundamental equations, and so many of you remember classical mechanics, force is mass times acceleration, or quantum mechanics, the rate of change of the wave function is the Hamiltonian times the wave function, or electrostatics, the Coulomb's law, the gradient, the divergence of the electric field is the charge density. Radiation transfer is the same way. It has a fundamental equation which is seldom written down. That's a bad idea because it means that you make mistakes if you don't understand where you're starting from. So let me show you the equation for radiation transfer. Here it is. This is called the equation of transfer. It goes back to astrophysics. That's where it was invented. So the basic state of the radiation field is the intensity of radiation. So the intensity depends on altitude. I'm talking about the Earth now, but it could be a star. So it'll depend on the spatial coordinate and also the direction, because radiation can go this way or that way. And so the direction is measured by the direction cosine if you have, say, axially symmetric radiation going up to space from where we stand here. So I'm not going to spend a lot of time talking about this, but let me just force you to look at the equation a little bit. I don't like to look at equations either, but the equation has a opacity of the medium through which the radiation is going. So alpha is the attenuation of the radiation. If you've got radiation that's going directly up, then it has less material to go through than if you go at a slant direction. So you have to account for the direction that the radiation is going with this direction cosine of the radiation. So the first term shows the destruction of radiation, the attenuation. The second term is the generation. So as you go up through the atmosphere, or if you come out of the Earth, radiation is being generated at a rate proportional to the Planck intensity. So this was invented by Max Planck in Germany 100 years ago, a little more than 100 years ago. Very, very important. Here's Planck's formula for radiation. It's a funny formula. It was actually guessed, by Planck, and then he was able to explain why it made sense, and now we know it makes perfect sense, but wasn't so obvious when he proposed it. And finally, there's scattering, radiation going in at this direction on a snowflake, for example, can scatter into another direction. And so now, turns out scattering it seems very plausible, but it's completely irrelevant to greenhouse gases. Greenhouse gases do not scatter radiation. They only absorb radiation and re-emit like Planck emitters. So this term is missing for greenhouse gases, thank goodness, because it's the most complicated term in the equation of radiation transfer. So with no scattering, the equation is much simpler. It says the rate of change of the intensity is attenuation and then regeneration by emission. And again, you notice there's the attenuation and there's this factor of slant direction that makes slant rays go through lots more material. You have to take that into account to get the right answer. Slant paths are much longer. So radiation transfer in the Earth is really determined by opacity, and that's concentrations of greenhouse gases, mostly water vapor, but CO2, methane, nitrous oxide, ozone, and by temperature. Both are important. If the Earth had the same temperature from the surface to outer space, you could add all the greenhouse gases you like. It would make no difference. So the temperature variation from ground to space is very, very important in calculating the effects of greenhouse gases. So here is a summary of these two things that affect greenhouse warming of the Earth. One is the temperature profile. So temperature is plotted here in Kelvin. So we're sitting here just under 300 Kelvin in this room. And this temperature drops very rapidly. That's why if you go to the mountains, it gets colder rapidly as you go up until you reach 10 or 11 kilometers in Germany. And that's the tropopause where the cooling stops and the temperature is flat and then begins to rise again. And so in this region of rapidly dropping temperature, there is massive convection. Parcels of warm air come up from the surface, often carrying moisture. They condense, they make clouds, they cool off, cold air falls down back to the surface again. It can be complicated by inversion layers, all sorts of complications, but a sort of overall average looks like this. And so the typical temperature drop is around 6 or 7 degrees centigrade per kilometer. Now here are the greenhouse gases that everyone is worried about. And by far the most important is water vapor, this blue curve here. So this is altitude, 20 kilometers, 40 kilometers. And water is confined to very low altitudes. This is a logarithmic scale, so every tick here is a factor of 10. So water rapidly, becomes less important as you go up because it freezes out as rain and snow. CO2 is this red curve here. CO2 is pretty well mixed. It begins to disappear as you get above 90 kilometers because it gets dissociated at higher altitudes. Ozone peaks actually in the stratosphere because it's created there by ultraviolet sunlight. And so ozone is made in place in the atmosphere. some of it gets to the surface. But if it's really the stratospheric part that's most important, then methane is being reacted, so it slowly decreases in concentration as you go at nitrous oxide, same way. All right, let's see. This is not advancing for some reason. Now, I want to make another point here, and that is you see a lot of models. When people talk about climate, you see lots of models. And some parts of the models are very good. For example, the temperature profile, this is a real profile measured by a balloon. It actually looks similar to what I just sketched for the troposphere. You know, it's dropping at roughly 6.5 degrees per kilometer with some glitches here and there. But the water content is completely different. Water never looks like like what I showed you here. This is nice smooth curve for water. Nobody has ever observed that. And this is important because most of the warming comes from fiddling with water vapor and water vapor feedback. So that is by far the most unreliable part of climate models, and it's the one that is in worst agreement with what you observe. Nobody really knows exactly what water is doing. So remember that when people tell you how good models are. Well, here's an example of solving radiation transfer. If you're deep below the top of the atmosphere, radiation isotropizes. So you see radiation coming from every direction because it's very much like if you flew in, as I did, to Gera yesterday, you flew through clouds. If you look out the airplane window, everywhere you look, you see white clouds. The radiation intensity is the same in all directions. And so that's characteristic of Planck radiation, thermal radiation. Of course, you can't see the thermal radiation, but it's isotropic. As you move toward the top of the atmosphere, there's less downgoing radiation because there's not much material left above you, so you see less downwelling than upwelling. And when you finally break through the top of the atmosphere, it's all upward radiation. The other interesting thing that you calculate and observe is that the radiation going directly up is more intense than the radiation going sideways. This is the famous limb darkening that you see so often in stars, especially our sun. And the reason is that the temperature is dropping as you go up, so the horizontal radiation comes from higher layers in the sun, and the vertical radiation comes from deeper layers in, well, the Earth's atmosphere or the sun. So here is a picture of limb darkening of the sun. So if you look directly at the center of the sun, which of course you shouldn't do without protection, you see some sunspots, but as you go out toward the edges, the sun gets quite a bit dimmer, and the color changes too, because you can judge temperature from color. And that's because the radiation in the center is coming from deep inside the sun where it's hotter, and the radiation from the edge is coming from the very top layers of the sun, of the photosphere, where it's quite a bit cooler. And so the radiation is less intense. The Earth's radiation also does this. There's a lot of limb darkening. Okay, so here's sort of the one chart I want you to remember of this talk. This is the most important one of all. And this was born and bred in Germany, so I'm really honored to talk about it in Germany. And here is Max Planck. And this is the famous Planck spectrum of a black body, this blue curve. And I showed you a formula for it, but this is what it looks like if you plot it versus spatial frequency, waves per centimeter. And that's what you would see if you looked down on the Earth and you had a transparent atmosphere with no greenhouse gases, only nitrogen and oxygen. But if you look down from the Earth in reality, what you see is this black curve, and I'll show you in a minute some satellite pictures that look almost exactly like the black curve. And so I like to call the black curve the Schwarzschild curve. This is in honor of another great German physicist, Karl Schwarzschild, who did the first analytic solution of Einstein's general relativity equations, but he also did some of the pioneering work on radiative transfer soon after Planck's work became available. People sort of knew about radiation transfer before Planck, but it wasn't until Planck came along that you could make it quantitative, and that's what Karl Schwarzschild did. So very sad. You can see he died in 1916. That was during World War I. He died on the Russian front, but not from a Russian bullet. He had a terrible autoimmune disease that finished him off right in the middle of the First World War, a real tragedy because he was so creative. But his black curve is here. It's these jagged lines, and the reason it's jagged is because of all of the greenhouse gases. I've marked the ones that are responsible for the jags at different frequencies. CO2 is very prominent here, but it's really only of secondary importance compared to water. So water dominates here. So the water is the reason for the difference between the blue curve and the black curve here. Water is the difference between the blue curve and the black curve here. Methane and nitrous oxide you hardly can notice. Ozone is quite important. This is ozone here, but this is coming from high up in the atmosphere. It has little direct effect on the surface. But the important point about the scale is if you were to take CO2, which is around 400 parts per million now, and double it to 800, what would happen to this curve, which showed radiation coming out of the Earth into space, the cooling radiation, go from the black curve to the red curve? You can hardly see the difference. So this is what we're going to spend hundreds of trillions of dollars for, is because of the difference between this black curve and this red curve. That's the radiation. IPC completely agrees with this, but they don't show you this curve because it wouldn't be alarming enough. So the radiation, the cooling radiation going to space is the area under these curves. So without doubling CO2, it's 277 watts. With CO2, it's 274, so it's a 1% decrease. So doubling CO2, 100% increase, decreases the cooling radiation by 1%, a little more than 1.1%. And you have to scratch your head, why is this a climate emergency? Well, we can, in a little bit, I'll tell you what this implies in terms of temperature. The real answer is nobody is quite sure what it implies about temperature, but it's certainly not very much, nothing to be worried about. Okay, so that's the reason for the title, Much Ado About Almost Nothing. The almost nothing is the difference between the black and the red curves. Everywhere else on this chart, black and red are overlapping, and so you can't even see the difference. And we have this tiny difference here because of doubling CO2. All right. This is really the same mechanism that makes the Fraunhofer lines of the sun. Another German, whose enormous contributions to physics. And if you look at the sun, you see this beautiful rainbow, but in addition to the rainbow, you see these dark lines, which Fraunhofer was the first to discover and use. Fraunhofer was famous for making achromatic lenses, and so he actually used these lines as calibrated wavelengths, as he was designing lenses that got rid of chromatic aberration. A very bright guy. But these lines are produced in the same way as the jags that I showed you in the previous slide. They're by atoms and ions in the outer layers of the sun. This is the famous sodium yellow D line. Out here, the C line is from hydrogen. That's Balmer alpha. There are some lines from iron here, more from hydrogen. But it's a lot easier to work with the Fraunhofer lines than it is with greenhouse gases. And the reason is you can count the number of lines here on, your hands and your toes. There are not many of them that are important. But if you go to greenhouse gases, here are the main greenhouse gases. There are hundreds of thousands of lines, there are literally millions of lines that have to be taken into account because the absorption is due to the tumbling and the vibration of these molecules. So this gives you a feeling for what the problem is. So if you're doing radiation transfer for the atmosphere, here's the main greenhouse gas, water, hundreds of thousands of lines, hundreds of thousands of lines for CO2, even more for O3. The heavier it is, the more lines they have. Nitrous oxide, methane, all of those have to be taken into account. If you don't take them into account, you don't get the right answer. But if you do, it's amazing how well it works. Okay, greenhouse effect is the same thing that Fraunhofer observed, but with a lot more complexity because of the rotation vibration spectrum. I mentioned how well these work, and so this is a comparison of modelings I did with William van Wijngaarden. These are model spectra coming from the Earth upward. So the dashed red curve is a Planck curve. The blacks are jagged lines or model lines. This is what's measured with the satellite. These are absolute scales, same absolute scale, no fitting, just taking the measured temperature profile of the Earth and solving the Schwarzschild equation, radiation transfer equation. So it really works very well. It's hard to tell the difference. And this is for different parts of the Earth's surface. Up here, for example, is the Sahara Desert. So if you look at this is frequency of the radiation coming out in waves per centimeter. And so over the Sahara, you can see the hot desert sand here. It's quite hot. It's not quite body temperature, but it's close. Model looks the same way. This is ozone absorbing radiations. This is carbon dioxide, water vapor. This is a little bit cooler. This is over the Mediterranean Sea. And if you look at the scale here, it's not quite as hot. The most interesting part is over Antarctica. So over Antarctica, the surface is so cold that most of the water has been condensed out, so the effects of water are much suppressed over Antarctica. You hardly see it at all at these high frequencies, and this low frequency rotation band you can just barely still see. And all of the greenhouse gas emission is the other way. So greenhouse gases over Antarctica actually cool Antarctica. So they produce more radiation coming from Antarctica than Antarctica could radiate without greenhouse gases. So the sign of the greenhouse gas warming and cooling reverses somewhere between mid-latitudes and Antarctica. But interesting thing is what you calculate and what you observe is the same. So that's one of the reasons that I think one can be pretty confident that calculated changes in flux, at least, are very reliable. So here are some examples. Just to remind you, here's the temperature profile of the Earth, rapid cooling to the tropopause, an isothermal region, and then warming to where the ozone absorption gives another temperature peak. And here is the upward flux of radiation versus altitude. Now, if there were no greenhouse gases, you would get the Planck flux here, which is around 400, just under 400 watts per square meter. But because of greenhouse gases, you get much less than that close to the Earth's surface. So close to the Earth's surface, the heat transfer is a combination of convection and radiation. It's about half convection at the surface. Convection gets less and less as you go up. So the difference between the actual radiation curve here and the extrapolation down here is the convective part. And by the time you reach the tropopause, the convection has stopped. That sort of defines the troposphere, is where the convection stops being important. Everything above is pure radiative transfer. It still increases a little bit because of this ozone absorption, but that's an important picture to, again, have in mind, that the radiative flux increases. And this increase, by the way, you have to conserve energy. So this means that over most of the atmosphere, radiation is cooling the Earth. How much time do I have? No more. Okay. Thank you. I will stop here. I've made all the main. Well, let me make one last slide here. Yeah. Okay. Okay. So this is important. So there's a zero-order estimate of warming. So I just showed you that if you double CO2, you decrease radiation to space by about 1.1%. Okay, if you assume that you have to make that up to keep the Earth from warming too much, then you get, you conclude that the temperature change, since it goes as the fourth power, the change in temperature has to be a quarter of that, a quarter of 1.1%. The absolute temperature is about 300, so the zeroth order estimate is about 0.8 C for doubling CO2. So I'm willing to bet, in 50 years, when the answer is actually known, that it'll be a lot closer to this than it is to IPCC models. So I'll stop here. Thank you for your patience.
Herzlichen Dank. Vielen herzlichen Dank. Und wer meldet sich? Wer möchte was dazu sagen? Ja, ich komme.
As far as I understand it, CO2 is not only absorbing the radiation from the ground, it also absorbs heat from other molecules in the atmosphere, and then you have the radiation into the sky, so to get the cooling. So if you increase this concentration of CO2, you not only have to take into consideration more absorption in the ground, but also more radiation up on in the down in the sky, and so I would like to know: is it ever calculated what the effect is more greater?
Yes, I had a slide I had to skip on that, but I'll tell you in words. So if you, for example, follow the Manabe prescription, Manabe got a Nobel Prize. It's very surprising, but anyway. The basic physics he used is called the radiative convective equilibrium. And that says that after you've doubled the CO2 concentrations, you readjust the temperatures of the atmosphere until you restore the same amount of energy going out as it's coming in from the sun. If you do that, you find that the surface has to warm by a little more than a degree, for example, 1.4 degrees. And the stratosphere has to cool by nearly 8 degrees. So the effect of restoring convective radiative equilibrium is to change the temperature by different amounts at different altitudes. You warm the surface, you cool the stratosphere. That's because, stratosphere has more CO2 that's taking radiation to space, so it's cooling it faster, so the temperature drops in the stratosphere.
Oh, does it work? Okay. It seems to me that you, so to say, include latent heat in the convection. I mean, the main transport of heat from the ground or from the sea level to high altitudes is by latent heat, by the evaporation of water and then condensation at higher levels. So you include that in there because you didn't really mention it.
Well, I think I'm at least touched on moist convection when I said that people can sweat, to get a little more heat transfer. But yes, you're right. If the convection from the surface up, a good fraction of the heat, more than half, is from latent heat of water. And as the air moves up and cools down, the water condenses and releases the heat. And so that's what slows down the lapse rate. You know, if there were dry air causing convective cooling, it would drop at a 9.8 centigrade per kilometer. But with water vapor, it's much slower because heat is released as water molecules condense to form snow and liquid. And so, absolutely, and the other important point about that is that you can be sure that whatever is happening will change the cloud cover. And that's not really taken into account very well by models. It's purely guesswork. But very likely the changes in cloud cover will be at least as important as the direct effects of more greenhouse gases because of this convection that you mentioned.
Unfortunately, you had to take the fast track to the conclusion. My understanding is doubling CO2 leads to less than 1 degree Celsius temperature increase. What makes it, that's the question now, what makes it so difficult to convince the IPCC guys? Should I repeat the question? Okay, the conclusion is a doubling of the CO2 leads to less than 1 centigrade Celsius increase. What makes it so difficult to convince the IPCC guys?
Well, look, the reason they are predicting much larger warmings is because they've invented positive feedback. They have, the reason they get these much larger temperature rises is from positive feedback, mostly from water. And so that's not being observed. You know, they have to make assumptions about water vapor changes in response to surface temperature changes that are not observed. For example, Manabe himself assumed that relative humidity did not change, you know, so that caused lots more water to be in high altitudes in his models, and that, you know, doubled the warming without that. But that's not what's observed. All of the observations of water vapor show that there is, if anything, there is drying of the upper atmosphere, not humidifying of the upper atmosphere. So none of it holds together.
Thank you very much. Sie möchten noch ja, aber die allerletzte und bitte, bitte, bitte kurz.
As you showed in the Schwarzschild curve, the most contribution of the CO2 comes from the 15 micrometer absorption band of the CO2. And the process of radiation transfer is an absorption and re-emission, maybe 100,000 times to get the radiation out. Here in Germany, there was a big discussion about the so-called back radiation, not the backscatter radiation, the back radiation of some amount. Can you tell something about this?
Ja, Moment.
Okay. Could you repeat what the, yeah. Thank you. Would you mind repeating what the discussion was about? I got the 16 microns right, the many scatterings, I got that. But what was the discussion? Oh, you're talking about the upwelling and downwelling radiation? Okay, well, as I showed on those graphs showing the directions of radiation, near the surface, there's equal amounts of up radiation and down radiation. You know, they're the same. So you don't carry any energy when you're close to the ground. You only get energy transport near the top of the atmosphere where there's only one optical depth left between you and outer space. So that's where all the action is. It doesn't matter at lower altitudes. And why people talk about upwelling and downwelling beats me because, you know, you don't do that with electrical current and resistors. You know, there's natural current flowing left and right in a resistor, but you only worry about the sum, the algebraic sum. But for some reason in climate science, they talk about upwelling and downwelling, and the fact that it's really the algebraic sum that counts doesn't get discussed. I mean, it's okay to do that, but it simply strikes me as not very efficient.
Okay. So we must stop now. Yeah.